Okay, so I think we're going to start, everyone. Thank you all for coming to this session. So this is the session on morphology and science. So just before we start, I'm sure you're aware of it now, but I want to point out again, there is a code from that which you signed up for when you registered, and we will contact them. I think at this stage, anyone online who cannot hear, now would be a good time to complain if that's the case. But I think we're going to start straight away with the impression. So, sharing. Yeah, so the microphone's on too. And for all the speakers, I will give a 2-minute warning after the 12 minutes for your talk.
Hello everyone, my name is Unnikrishnan. I'm a postdoc at the University of Witwatersrand in Johannesburg, South Africa. Thanks a lot for the organizers. I'm really glad to be here and present my work that I recently started with my collaborators listed here. So in which Agnieszka Polo is also attending the meeting in person. So this work deals with the tracing the environmental dependence of laws of surprise galaxy properties. So to start with, we have a dedicated session for laws of brightness galaxies. So these galaxies are defined as those having their surface brightness fainter than the night sky. So since they account for a significant fraction of the total galaxy number density, so they play a crucial role in the galaxy evolution. So the main question that we have are like, do these galaxies evolve differently from the normal galaxies, and does the environment play a crucial role in their evolution? So what do I mean by environment? So in the right plot, you see the Lasky structure mapped by SDSs, and we can clearly see that galaxies live in different environments, where you have more dense environments and less dense environments in the Lasky structure. So the environment of laws of brightness galaxies has been studied a bit in the past, where these are the few results I'm quoting their results, and where most of the studies have found that LSBs, that's the laws of brightness galaxies, prefer low density environments. So in addition, my collaborator Junais also found in his work that the galaxy Malin 1, which is the largest LSB, is found in an isolated environment. So all these results together tell us that LSBs galaxies prefer underdense environments. So this is something that we want to check in this work using LSBs from the dark energy survey. So we do have a sample of LSBs identified using Cirrus model fitting by Athanolidis and team. And then later, my collaborator, who is a PhD student in Warsaw NCBJ, Harish Tirthipalli. So in this work led by him, we identified about 4,000 more new LSBs that added to the sample of LSBs available for us. Now, this is the sky distribution of the LSBs that we have, and we can clearly see that the distribution is not random, and there's clustering in the distribution, and importantly, the clustering is more prominent in the red. If we divide this sample into red and blue LSBs, then the clustering is prominent in the red side. So which means that the color is correlated with the clustering of these galaxies, and we want to quantify this. So to quantify the clustering, we use a tool called Galaxy 2-point angular correlation function. So I will quickly introduce angular correlation function. So it is a function of the angular separation between galaxy pairs in a sample, and it basically compares the real distribution of the galaxies in the sky to a random distribution, and then quantifies how strong the clustering is in the real distribution. So this is just for a demo. If you look at the red sample, you see more clustering patterns here, and then the resulting 2-point correlation function gives a stronger amplitude compared to the blue one, which has less clustering And then if the distribution is random, like the green ones, you see the 2-point correlation function around 0. So this, which means that 2-point correlation function is quite a good tool to quantify the cluster. Now we use this tool for the LSB sample, and we measured the 2-point correlation function and compared it to the HSBs. So HSBs means high surface brightness galaxies, which is on the other side of the surface brightness regime, which is at surface brightness less than 24.2. So what we find is that the LSBs are more clustered than the HSBs. And also when we divide this sample, both the samples into red and blue, we see that for the blue LSBs and the blue HSBs, the clustering pattern is similar. But for the red and LSBs and red HSBs, the red LSBs show a stronger clustering pattern. So which means that these galaxy properties are correlated with this clustering in a complicated way, and we wanted to quantify it further using another tool called marked correlation function. So in marked correlation function, we can use any property of these objects to weight the galaxies, and then using this weight, we compute the weighted 2-point correlation function. Then using this estimator, we compute the marked correlation function. So the key idea is that if the marked correlation function value is greater than 1 for a given galaxy property, which means that that property is strongly correlated with the environment, which means for the galaxies in that sample, the galaxies with the higher value of that property are strongly clustered. And the other way, if it is less than that. So these are a few interesting applications of marked correlation functions, which we did with galaxies from the Gamma survey. So if you are interested, please go and check these out. So when it comes to the DES sample we have, so this is the marked correlation function measured for the HSBs and the LSBs for the color, surface brightness, and magnitude, and the effective radius. So as you can see, if you compare the color marked correlation function, which are these squares, you see that both have a stronger correlation, which means that the galaxies with the higher value of G minus I color, which means the galaxies which are redder, are strongly clustered. But that is not something new. We already know that from the normal 2-point correlation function measurements as well. But when it comes to the surface brightness, which are these triangles, we see that in case of the high surface brightness galaxies, it is anti-correlated. That is, the galaxies with higher value of the surface brightness is least clustered, which means the galaxies which are brighter, because the magnitude brightness trend opposite way. So the galaxies which are brighter are strongly clustered in terms of high surface brightness galaxies, which is again not something new, which we already see. But when it comes to the LSBs, we see the trend is opposite. We see that the galaxies with higher, which are brighter in the LSBs, are least clustered, which is entirely opposite to what we expect. So we also check if we divide the sample into red and blue, do something change, and we see that between the blue and red populations, the signals have difference. We need to look this into details. So we also check what's happening within the surface brightness. So what we did is like we bin the entire sample of LSBs and HSBs together into bins of surface brightness, and then compare the normal unweighted 2-point correlation functions. So as you go from the brightest to the faintest, you see that the amplitude reduces, and then at some point it goes up. So this is like, when we fit it to a power law and then compare the amplitudes, we see the effect of a reversal of the trend in the clustering dependence on the surface brightness.
Could you try to speak a bit louder towards the microphone? Sorry,
Okay.
I think people can't hear you.
Oh, okay.
Don't worry.
Sorry about that. So at least you can hear my conclusions now. So to conclude, what we observe is that the low surface brightness galaxies show a stronger clustering than the normal galaxies, and within them the red LSBs cluster differently than the blue ones, and the blue LSBs show a similar clustering behavior as the blue HSPs, but that's not the same with red LSPs and the red HSPs. Also, interestingly, we see a reversal of the clustering dependence on surface brightness from the HSB to the LSB regime. So this is a very new result that we have right now, and we are yet to figure out if this is a real, if there is a physical reason behind this, or it has something to do with the selection effects. So of course, in future, when we have more LSB detections by LSST, we will definitely have a better understanding of the science behind this effects. So before I finish, I would also like to talk about the in-kind contribution to Rubin from South Africa, which I'm part of. So this project is designed to deliver high-level Meerkat data products into the Rubin platform. So we plan to take the public data available within the Meerkat radio telescope and then get sources out of them and cross-match them with the Rubin when the Rubin is available. So we plan to deliver the radio continuum images, catalogs, all the cross-matching tools that we develop, and the cutouts to the community. So this is the footprint of the Rubin, in which these dots are where the public data of Meerkat is available. And with the resulting catalog, cross-match catalog, there are quite some science outputs possible, like the same environment dependence what we saw in the previous works. We can do it in the radio as well using the catalog. Also, we can have just unobscured star formation rates of these galaxies and so on. So if you are interested, please get in touch with me or Marc. Marc is a PI of the project. And then also you can get details from this website. Also, I would like to, being an external collaborator of the National Center for Nuclear Research in Warsaw, I would like to advertise this a few postdoc and PhD positions. Agnieszka has already done this yesterday as well. So yeah, so these are very good positions available to work with Agnieszka, Kasia, and Will. And if you are interested, please go ahead and apply, and we can work on things together. And Warsaw is a beautiful city to live in. Okay, so I will leave here. Thank you for your attention.
So, any questions?
Yeah, you mentioned selection effects, and I'm just wondering if you have thought about this. So it's well known that detecting low surface brightness galaxies is a challenge, mostly due to selection effects, because of the fact that it is dependent on the measurement bias. So there's somehow you get the photometry of the low surface brightness galaxies, and exactly how you do that photometry can introduce a surface brightness selection effect. Mm-hmm. And I'm just wondering if you thought about that. It seems to me, looking at your results, that that goes in the wrong direction, which is good news. But it's all related to this. You may have a different measurement bias in the dense areas than in the undense areas.
Yes. So till now, what we checked is the difference between different the code that you use to do the circuit fitting, like alpha and extractor, and between them the results are consistent. But other than that, we haven't explored any other effects yet. So this is relatively new thing, and we are yet to do that. Thank you.
So we can take one more question, I think. Okay. Yep.
I was wondering if your correlation functions here, if it's in the one tail or the two tail regime.
So yeah. So if you look at this correlation function, so these are angular correlation functions, and for the redshift, so we have the photometric redshift for this, and then we put a cut of 0.1. So the corresponding the 3D distance would be around like this. This scale would be around the typical scale of a cluster of a halo. So we do have both the terms in this correlation.
Okay, great. Thanks very much.
You.
You want to plug into this?
Thank you.
Cool. Thank you, sir. Go ahead.
Hi, everyone. My name's Sarah Brough. I'm at the University of New South Wales in Sydney. And I'm here today to talk about intracluster light. So intracluster light is an example of it on the left-hand side of the slides, where this is the extended diffuse stellar light at the center of galaxy groups and galaxy cluster halos. So, and in this talk, we're very LSST focused. So this is the telescope, which is under construction, looking very pretty from about a year ago. And when I talk about intracluster light, I really make the point that intracluster light is a bit like an iceberg, in that we know that 10, maybe 60% of the total stellar mass in galaxy groups and clusters is held in this component, but we know very little about it so far. So we really need to understand more. We need to see the bottom of the iceberg. So this is the classic, hopefully the video will play, excellent. The classic intracluster light video. This is a simulation from a PhD student of Chris Mihos, and showing the galaxies at the center of the halo, bashing themselves together, stars falling off, being ripped out, or the galaxies being destroyed, and those stars kind of falling to the center of the halo and sitting at the bottom of that potential. They're not necessarily bound to that central galaxy, but they're present in that location because that's where the center of the gravitational potential is. So we know that as galaxies merge and they transform in halos, that process isn't completely efficient. So it's not like one galaxy plus another galaxy equals a new galaxy of 2 galaxy size. It's often new galaxy of slightly less than 2 galaxy size. A lot of those stars were ripped off, and that mass is lost to the new galaxy. And that means that the intracluster light provides this really important, quite interesting fossil record of those interactions that have occurred, and of what fraction of mass has ended up there. I got into this because I think this is a really crucial part of our understanding of the evolution of brightest cluster galaxies. I think from about 10 years ago, we're really limited in our understanding of the evolution of the galaxies at the center of these systems, because we don't have this additional information about the stars that have been lost in that merging process into this component. So what is intracluster light and where does it come from? Well, we still need to understand that. And to understand that, we need to answer the questions of when and where does it form and from which galaxies. We can answer that by measuring the quantity and the distribution of that intracluster light, and by establishing the relationships that that quantity holds with cluster mass, which tells us about where it formed. Is it forming around single galaxies? Is it forming in galaxy groups? Is it not forming until it gets to something the size of a galaxy cluster? Looking at the relationships intracluster light holds with with redshift tells us about when it formed. Did it just form quite recently, just the last half the age of the universe, or has it been going on since the beginning of time? And we can look at the color distribution of this component, and that can start to tell us which, very coarsely, but it can give us an idea about which galaxies contributed their stars on the whole to this component. So, and then obviously there's always a really important component where we have limited information with our observations. We really need to compare our observational understanding with cosmological simulations to try and understand the physics behind what we're seeing. Why haven't we answered all of this yet? Because these aren't hard questions. That's because this component is stupidly faint. it's around a 600th of the brightness of the dark night sky. So no moon, dark night sky, 600th of the brightness. So you've really got to dig into your noise very carefully, very precisely to be able to observe this stuff. Robert's like,
Well, it's not the noise, it's the systematic.
oh.
Noise is also an issue. Go on.
Keep going, Sarah.
I'll just plow on through. So we need more data. So people have observed this, but it's been very pointed studies, single clusters. So we have information, but we need statistics now. And that's where LSST is going to come in and just be amazing. I include a slide on this, and I realize I can totally have taken this up at this conference. So, you know, it's going to be amazing. We've got some really nice, Peter Joachim used some of the survey simulations to go through and estimate the limiting surface brightness that LSST will have after its 10 years of observations. And with that, we're looking at sensitivities of about 30.3 magnitudes per square arc second in LSST. So really beautifully faint data we hope we can get to. So what's stopping us now? We're going to get our data. Well, there's still some hurdles. This is a research area, and it's a relatively on the cusp of getting to statistics. And so one of the things that shown quite nicely in this intracluster light review paper from Maria Montes in 2022 is that the relationships that we see from the existing studies, they're observed to depend on measurement method and or sample. So this plot here, it shows there's two panels that shows intracluster light fraction. So this is the light held in the intracluster light fraction as a function of the whole of the cluster. And it's compared against the halo mass. And on the left-hand side, the data have been measured using a particular measurement of intracluster light composite models. And on the right-hand side, by a different method, surface brightness cut. Now, you don't need to understand those two methods, but you can look at these data sets and see on the left-hand side, we have a variety of samples. On the right-hand side, really just one. But there are different relationships seen. These are kind of things that fill a researcher full of horror. I don't want to use different samples and different methods and see different relationships. I want to see the same relationships, no matter how I measure this component. So this is a somewhat of a concern. We see the same thing with redshift. So when we look at intracluster light fraction as a function of redshift, we see slightly different relationships with redshift, depending on whether we're measuring with composite models or surface brightness cuts. Now, the data that go into this is very heterogeneous. It comes from different samples. That could be one element, or there are these different measurement methods. So let's start by asking, how should we measure intracluster light? What is the best way of doing that? There's about 5 standard methods that people use in the literature at the moment. I won't go into great detail, but I'll just say that there's kind of, you know, ranges from the simplest of a curve of growth, which captures both the brightest cluster galaxy and the intracluster light as it goes out, standard kind of aperture fitting. Sometimes we use a surface brightness threshold where we take, cut out the high surface brightness light in any image and only capture the light that sits below that. People use composite models that combine Cirrus and exponential fits to try and model the galaxies, subtract those and leave the intracluster light, or describe that with an exponential fit. Multi-galaxy fitting, which is kind of simultaneous, slightly more sophisticated, simultaneous modeling of everything, or wavelet decomposition, where we're kind of slightly forest-like approach, where we're kind of going down from the brightest levels and taking out those components until we're kind of left with the larger extended models. Each of those have pluses and minuses. Some are easier, some are harder. They have different systematics, but this is the mix we have available to us. The question I wanted to ask was, how does the intracluster light that we measure depend on the method we use? And to undertake that analysis, we used LSST light mock R-band images from hydrodynamical simulations, all of around the same halo mass. We didn't want to we wanted to take out any effective halo mass dependence, so there were around 10 to the 14 solar mass clusters from 4 simulations, including the ones Garreth works on, Horizon AGN. This is all published in Brough et al. 2024. So going into this, I honestly thought that there would be a simulated measurement of intracluster light. It turns out simulators discuss how to measure intracluster light fraction as actively as observers do. But so we have several simulated measurements from the 3D mass cues from these simulations. So we have a simulated BCG plus ICL fraction, which is a 3-dimensional aperture out to a 1 megaparsec radius. And then we also have an intracluster light fraction where the BCG is subtracted by using a central 3D annulus of various radii, 30, 50, and 100 kiloparsecs. And then also a kinematic decomposition where, which is shown slightly on the right-hand side, where kind of taking the velocity distribution of the particles in the system and decomposing those into those belonging to the galaxies and those belonging to the intracluster light. And we had 8 observers use their observational methods that have all been used on imaging surveys to date and ran those on mock images from those simulations and compared the observed method with the simulated method. So the first thing that we looked at was the BCG plus ICL fractions. This is a simpler method. And then here I show observed minus simulated method for the BCG plus ICL fraction. And what I'd like you to take away from this is that the measurement methods are surprisingly consistent with each other. There aren't huge offsets. There's a reasonable amount of scatter. And there's also a small offset with the simulated measurements, which speaks to the difficulty observers have with subtracting the satellite galaxies from the images. We can make it a bit harder. We can now start to take out the brightest cluster galaxy from that system. And once we do that, when we compare to the simulations, we find that the largest radius kind of subtracted aperture matched our observational methods better. We're not saying that's a physical answer, but empirically that's what we saw. That's the bottom panel of this slide. And again, there's not a huge amount of discrepancy between the methods, but now there's even more scatter, which really speaks to the difficulty we have with subtracting that brightest cluster galaxy and how you define that separation. And often many people don't actually make that separation because it just induces uncertainties. And we then compared with the kinematic method. And with the kinematic method, we have a large offset. So here the observed method using the images is offset by about half a dex from the simulated kinematic method, showing that we're really measuring very different quantities. So that's a slight concern and an area of interest, horror.
So about a minute.
I've got one total.
Yes.
Okay. Oh, damn it. So I'll just say the fact that there are lines drawn on this plot suggests that we can draw relationships between the kinematic and image-based fractions, but there's more to understand here, and we're working on this with a student of Garreth's, and I will stop there.
Thank you. So one question. Thank you, Sarah.
Yeah, so we know that BCGs are not often at the center, often not at the center of clusters, either spatially or kinematically. And so I'm wondering if you have given thought to finding the ICL completely independently of the BCG. And in fact, I'm curious, the kinematic offset,
Yep.
I would say, might be in fact an indication that you're really looking at what belongs to BCG.
So that's a whole other discussion.
Yeah.
Now, I would argue that a BCG that is outside of 0.25 R200 has recently fallen in from another system and isn't actually the true BCG of the system you're analyzing. And I will possibly fight to the death on that one.
I'll fight you.
I know.
but, you know, that's a long way
yeah,
up,
so-
it's in between.
So we find that many of them are at the center. There are slight offsets between the intracluster light and the BCG, but of order of 50 to 100 kiloparsecs, not 0.25, 0.5 R, 200. It's not substantial offsets. So
It's a continuous distribution compared to the X-ray.
yeah, so there's some nice, the new Euclid analysis of Perseus. There's actually a really beautiful example of this that I wasn't involved with, sadly. Recent paper led by Matthias Kluger. And so they show that a small offset between the intracluster light, center of light and the central BCG, but it's not centered around those, let's call them external BCGs. The kind of the more offset by kind of 0.5 R300, kind of like large radii. So I think,
Sir,
Yeah.
very brief yes/no question.
Yeah.
Did you introduce the night sky?
no.
before?
So we are in
That's
no
important.
way analyzing any observational concerns in this analysis. So this
Okay.
was very
Because that
much
could
around.
bias the results.
It could bias, but it won't bias this analysis, but it could bias future analyses, observational analysis of intracluster light. But it won't bias whether our methods are changing, our pure methods change in this sphere.
Thank you very much, Sarah. Okay, so hopefully you can hear me, Aleksandr. Feel free to start.
Maybe, but
Aleksandr, you're not muted. You are muted.
you are muted.
Okay, can you hear me now?
Yes, perfect, thank you.
Okay, great. So, yeah, so in this presentation, I'm going to talk about galactic cirrus in deep optical observations. And galactic cirrus represents diffuse clouds of gas and dust in our galaxy. And it is seen at different wavelengths, ultraviolet, optical, near infrared, far infrared, and there is also a correlation with the neutral hydrogen gas. And if we talk about optical galactic cirrus, then it is shown here as an example. Then we talk about starlight scattered of dust grains in our galaxy, typically located at high galactic latitudes. And they have small optical depth, and these clouds can be quite filamentary without any regular structure, and they can be quite bright even in regular images. And so we want to study galactic cirrus because first we would like to better understand the interstellar medium, the physics of the interstellar medium by probing the optical properties of dust grains and, for example, albedo and scattering function and different heating mechanisms, interstellar radiation field. And so this is very important for studying the interstellar medium in our galaxy. And another reason is that we want to identify and distinguish galactic cirrus from extragalactic low surface brightness features, such as low surface brightness galaxies, ultra diffuse galaxies, intracluster and intergroup lights, and of course, low surface brightness features around galaxies. And so our goal is to try to help identify some characteristics of galactic cirrus which can help us distinguish it from these extragalactic features. And so this is an example of a galaxy M81, specifically with the tidal feature ARPS loop shown here in this deep image. And it was thought to be a result of interaction of M81 and M82. These two galaxies did interact and they show some tidal features. But this specific ARPS loop, it actually belongs to our galaxy. So it's a part of galactic Cirrus in our galaxy, and it was shown in several papers using neutral hydrogen gas, velocities of gas, and dust emission. And on the right, you can see the large-scale cirrus surrounding these two galaxies and the optical. So a year ago, we published a paper on galactic cirrus in SDSS Trap 82. SDSS Trap 82 is a pretty deep source of optical images down to 28.5 magnitudes per squared second, the G band. And so in these images, we can definitely identify galactic cirrus. And so here you can see our methodology, how we select and annotate galactic cirrus in these fields. So first, if we have an original field with stars and galaxies and galactic cirrus, then we create a mask, and this was done automatically using a pre-trained neural network. And then for the mask data, we can create contours of a level of 29 magnitude per square second. Of course, some reviewing was done to increase the signal to noise ratio for these clouds. And then we can annotate clouds of gas, and this was done manually for a subsample of fields. And then we train a neural network to do this for the whole STRAP 82 data. We also subtracted starlight from these images because scattered light can affect the results of our analysis of galactic cirrus. And then the residuals is what we can basically study as galactic cirrus. And so these are some details of our neural network. If you're interested, you can refer to our paper, Smirnov et al. 2023. And so these are our results. And you can see here that there's a huge sample of filaments with different sizes. Most of them are very small. And the total area in STRAP 82 is 6.5 square degrees. The total area of STRAP 82 is 275 square degrees. And they are pretty dim, between 27 and 28 magnitude per square second in the G band. And you can also see the distribution of galactic cirrus across this stripe in right ascension and declination. So another thing we can do with galactic cirrus is measuring its colors. And since we have three filters, G, R, and I, we can measure two colors, G minus R and R minus I. And here we should be very careful because since we deal with very faint structures, then the error of our measured color increases with the decrease in low surface brightness for these features. And also the filament area can slightly affect our results. And we modeled this effect using mock images with galactic cirrus. And so this is a color diagram for galactic cirrus. So red circles here show our data, and green circles they show data from Roman et al. 2020, who studied galactic cirrus in the same STRAP 82 using the same observations, but they selected the largest filaments of dust in STRAP 82. And so you can see here that our results suggest that the color distribution for galactic cirrus is quite broad. And however, if we consider the total area of the filaments, then we can see that our results agree with the Roman et al. 2020. It is shown on the right, and we can see that the largest filaments, they do lie below this dashed line, which Roman et al. Found for the largest filaments in STRAP 82. But smaller filaments, they obviously show a much larger scatter of the colors. And so we decided to study this effect in greater detail using HSC SSP data, which are 1.5 magnitude deeper than STRAP 82 data. for the same portion of the sky, strap 82. And so the methodology is basically the same with some exceptions. And here you can see our preliminary results. How is this and HSCSSP compare? We can definitely see that HSCSSP is much deeper and more resolved, so that we get more structure of galactic cirrus with a larger number of filaments, whereas in SDSS, this is just a single cloud. And on the right, you can see that we also have a larger coverage of galactic cirrus for this intersected region of Cloud 82. So these are the colors from HSCSSP, and you can see that the distribution have become even broader. And this is also true for the largest filaments. And if we compare it with the Stripe 82 data, then we can see that there is a large fraction of galactic cirrus which overlap with the galaxies, which are shown here by blue circles. So definitely galactic cirrus is affected by some systematic effects like scattered light from stars, galaxies, and sky subtraction techniques, etc. But maybe there is some physics behind this fact that maybe the smaller filaments, they do have different colors. And so at the moment, we cannot conclude that galactic cirrus, it has different colors, different from those we observe for extragalactic features, but some further investigation is definitely required. Well, thank you for your attention.
Does anyone have any questions? Oh, yeah, go ahead.
I mean, this is a question maybe not just for this talk, but overall, and that is how, and since Robert is here, how how are studies of these sort going to interact with data management's work to really get down to these fantastically low surface brightness levels?
Okay, I see you, Todd. Sorry. You'll have noticed that that HSC image was over-subtracted. And that was done on purpose because when we didn't over-subtract, it messed up the lensing. So the algorithms were adjusted in that particular data set to deal with it. Now, Stripe 82 is special. And in Sloan, we ran an algorithm which was background matching. We successfully recovered the deep cirrus in the deep coads, and then you could start running these sort of things. So somewhere between those two is where we expect roaming to be initially. We may or may not have to deliberately remove power on reasonably large scales. And the IR Cirrus is out on the degrees scale, and that's really very hard to handle. How we tune things so that the ICL survives, but this IR Cirrus preferentially does at the larger scale IR Cirrus is not quite clear. But we will, and Jan knows quite a lot about this, I was talking to him, be expecting to recover large-scale backgrounds, possibly not for the early data release, and then explicitly remove them for the science cases that need them to be taken out. But it's tricky because for the reason Tony gave. For example, DES does a global background subtraction on the scale of each image by PCA. That doesn't work on Hyper Suprime-Cam because the A to D conversions don't work very well. So it really comes down to the details of the electronics as to how we're going to do it. So we're going to see the data and figure out how to deal with it. But I think the DM team are very well aware of these various angular scales where we're trying to do the science, but also what the technical issues are as to what we're going to hand over.
So I guess in this audience, I guess I'm curious whether there's a constructive way to have interaction between the community that's really interested in these low surface brightness features and the work in DM, and I'll say also trying to understand reflections in the instrument itself as well as part of the DM.
Ghost and Goody. Can I just say one thing before Sarah says the same thing, which is the low surface brightness group has a contributed effort from Aaron Watkins, who's directly working with us on quantifying things, and Sarah's group have contributed effort for wings and star wing subtraction. So there really is already a collaboration. She'll have more detail.
that was probably all I was going to say, but that regular interaction and Jan as well, kind of really engaging with people in DM we're really grateful for the fact that you're listening and responding. That isn't always seen in other projects working towards being able to do this. I'm going to add one thing before Garreth kills me, which is that in ICL as well, with so much data, you can just actually go which area of the sky has low cirrus, and you can chuck out the rest of it because we will already have so much statistics. You're able to do that. It's a privilege.
Okay, so I'm going to take the last question from Todd. I know there were people on Zoom who had questions, so I apologize, but maybe you can ask them in the Slack. Yeah.
Right, so the question, which I don't know how to proceed with, but the infrared cirrus, and that's because it's seeing the infrared, is very obvious in 350, 550 microns of Planck data. And at the brightnesses we're talking about, there's very low optical depth, and so it's linear in that
The angular
flux.
resolution is the problem.
Well, sure, but it gives you a start. You have things on sort of arc-minute scales, and if you're looking over a large area, you certainly have a template.
You
Planck
have a
data that you
template on an
should be
angular
able to
scale.
use somehow to isolate this.
We've thought about it.
I'm sure you have.
Okay, thank you very much. We're going to have to move on now to Catherine. So if she could. Okay, so thank you very much. Catherine, can you take it away, please?
All right. Hopefully everyone can hear me and see everything.
Yeah, great. Thank you.
Awesome. Okay, so today I'm going to be talking about a recent discovery around NGC 300, and I am a postdoc at the University of Arizona, and this is work done with the Delve Deep collaboration. Okay, so our current understanding of stellar halo assembly is definitely focused on the more massive regime. So at the mass of the Milky Way and larger, we know stellar halos are built up by accretion of lower mass systems. This falls into our standard picture of hierarchical assembly, where these mergers thicken the disk, trigger star formation. They can propel in situ stars out to large radii, but predominantly, this is mostly ex situ sort of process. And what's really great about this is that the long dynamical timescales in the outer regions of galaxies preserve the tracers of their evolution, right? So our Milky Way is the prime example where only 1% of the stellar mass of the Milky Way resides in the stellar halo, but it provides a wealth of information about the evolutionary history. However, at low masses, this is not as well understood. So there's been kind of this more recent question in the literature of maybe do dwarf galaxies contain stellar halos at all? Part of this is due in part to the fact that dwarf galaxies have a much lower potential, gravitational potential than more massive galaxies. So they're much more subject to both internal processes like feedback can disturb them a lot more significantly, as well as external processes like ram pressure stripping and so on. And currently, we don't have a lot of observational evidence to really understand exactly what's going on. And so we have this question of, if they do contain stellar halos, do they form like accretion, like in more massive galaxies? Or is it mostly from in situ stars that are radially migrating out from supernova feedback? Or even potentially dynamical heating from interacting with dark subhalos, so the very low mass subhalos that wouldn't necessarily host visible galaxies. So there's a little bit of evidence in the literature currently. So shown here is work from Jeff Carlin a few years ago, where a LMC mass galaxy seems to be interacting to some degree with this relatively massive dwarf. There's a stellar stream right here. There was no clear detection of a stellar halo around this dwarf galaxy. However, there is, suggestive that, it's interacting with something and likely pulling stars off of it. So what is Delve Deep? So in general, the Delve survey is a part of DES in a sense. So it's kind of the same area covered in the southern sky. And this is done on the 4-meter Blanco telescope. So Dull Deep specifically conducts deep G and I band imaging within close to the virial radius of 4 nearby and specifically isolated magenta cloud mass analogs within the local volume. So we want a 5 sigma depth about 1.5 magnitudes below the tip of the red giant. And then these are specifically the numbers for NGC 300. They vary slightly depending on our hosts. Our other hosts are NGC 55, IC 50, 152, and Sextans B. And this endeavor started in around 2019, and as of 2024, the imaging is complete for Delve Deep around all 4 of our hosts. And the reason why we want isolated galaxies is, of course, because they are not as clearly influenced by their other nearby galaxies. Okay, so NGC 300 specifically, it's an LMC mass analog. It is kind of your classic looking spiral galaxy. It's at the outskirts of the Sculptor group, meaning that it's probably not actually influenced by the group itself, as Sculptor is kind of this weird filamentary structure, and it's kind of right at the outskirts of it, but very close by, only 2 megaparsecs away. So if you've heard of NGC 300 before, it's probably because it is one of those classic examples of a perfect exponential disk galaxy at both luminosity and stellar density out to about 25 arc minutes from the center. And Delve Deep has very deep data now out to about 189 arc minutes from the center. It's not quite the virial radius, but very close to the virial radius of NGC 300. So this is an RGB map from the Delve Deep data around NGC 300. So the right panels are the actual point sources of all of things selected as an RGB. I'll show you that selection in just a moment. So these ellipses are 1 times R25 and 2 times R25. And you can actually see a little bit of the spiral structure popping out. The reason why the center is empty is just source density, so we can't recover all the sources right in the center of the galaxy, but that's okay because we're interested in the outskirts. Delve Deep is interested in understanding stellar halos as well as dwarf companions of dwarf galaxies. So the other 2 are also RGB maps that are smoothed in various ways. One is to emphasize the low surface brightness features, whereas one is showing more of the features close to the disk. And so I've labeled these features in a convenient way. That doesn't mean this is exactly what they are. We're still working on understanding exactly what's happening with the system. But you can see this very distinct stream that extends over 40 kiloparsecs from the center of the galaxy. And there's a bit that seems to extend to the south as well. We also have these kind of other detectable overdensities that we're referring to as shell 1 and shell 2. There's also this very clear dense region kind of outside of the disk of the galaxy in the inner stellar halo region. That just kind of stood out to me. We call it the diamond because it looks like a ring with a diamond on it. Okay, so here are a few CMDs of some of those features, not showing all of them, just for brevity. Overplotted is 10 gigayear isochrones with 2 different metallicities. These are Dartmouth isochrones for those interested. And note that our Delve Deep data is specifically in G and I band, which is why I'm plotting in G and I, which you might be used to G minus R instead. So the cyan box is our RGB selection box. And then, so this is a background region. I've taken several different backgrounds where they're either at the same distance from the galaxy as the feature. This specific box is a giant box within proximity of NGC 300. You can see there's very no clear detectable like RGB at our distance. And so here is the halo over density, and then this right panel is just the background subtracted CMD using this background here, where the halo over density, you can already tell, seems to be noticeably a bit more leaning more metal poor than say the stream is. And whereas, say, the shell feature seems to have more of a metallicity spread. So I've made some metallicity distribution functions using just a very basic interpolation to try to estimate the metallicity of these different features. And I've also overplotted as this background the halo region that isn't the halo overdensity. And so just comparing the halo region and that overdensity, they have very similar metallicities. There's just a lot more stars in that overdensity. And you can kind of see as you step through, the northern part of the stream is the most metal poor. The shells are relatively comparable. They're not quite as metal poor. And then that southern part of the stream is even less. And I would say part of that is at least due to it being very close to the more inner halo region. But overall, the inner halo has been studied a decent, or well, the outer disk, I should say, of NGC 300 has been fairly well studied. It is not any more metal rich than Fe over H of -1, and it leans more metal rich than that as you go towards the center of the galaxy. I might have said that backwards, sorry. And so all of these overdensities are certainly more metal poor than that. And so there's this thought of perhaps it is all one dwarf galaxy that has wrapped around and wrapped around again. If I add all of the luminosity of the different features together, which, this is still a work in progress, the total I band absolute magnitude is around -10. So I need to get the G band and then convert that to our classic, what we like to use, V band. But this is probably similar luminosity to, say, like a classical dwarf of the Milky Way as the progenitor. Of course, this is a rough estimate, as I need to account additionally for stuff that could be behind NGC 300 that I can't really detect. So it's really interesting because historically we thought NGC 300 is your classic exponential disk. There was an H1 study performed about a decade ago where they identified an inner H1 disk well aligned to the optical disk. However, there was a twisted outer H1 disk that was suggestive of tidal interactions. And so this kind of helps tie into that picture of this might be the interaction that could have caused such an effect. And so this delve deep imaging has now uncovered a large stellar stream in NGC 300's outer halo. It's more metal poor than the galaxy's outer region, which is directly indicative of an accretion event at the dwarf galaxy scale, for the first time showing, the halo seems to be built up at least in part by accretion. But clearly this is a lot more complex, and there's a lot more that can be done with this, dynamical modeling, all sorts of fun things. But then looking to the future with LSST, and so this is just a fun another RGB map where I've split on an Fe over H -1 isochrone. And you can see a lot of the outer region is clearly all of these more metal poor things that were likely accreted than the more metal rich stuff towards the center of the galaxy. So I mentioned delve deep a little bit, but so we covered 4 dwarf mass galaxies to sufficient depths to study their halos over about 20 nights per galaxy, and it took over 2 years-ish per galaxy. And so in comparison, the LSST depths, especially the 10-year 5 sigma point source depths of the coads, will allow us to characterize stellar halos of all dwarf galaxies within 6 megaparsecs to really start addressing the question of dwarf galaxy assembly. And, this is only 4 galaxies we looked at. We could look at, hundreds in this sense, and a little bit further out than what we've been able to do with Delve Deep as well. Now, there are, of course, some caveats, but there is work underway with the star galaxy separation, as well as low surface brightness detection optimization. The ongoing work by Jeff Carlin and Peter Ferguson are using CNN identification of these kind of low surface brightness streams, because when we have so many galaxies that we're looking at, we're going to want to use this to actually figure out which ones are interesting that we might want to further address. So that's everything for now. And feel free to let me know if you have questions. And if you scan this QR code, it will take you to my website if you want to further contact me.
Thank you, Catherine. Time for a question. Anyone on that? Okay, I have a question then. I wonder, are there any objects that could be progenitors for the streams that you see, or are you assuming that they are just merging with the dwarf?
Yeah, no, that's a fantastic question. So I first had the thought, oh, maybe the overdensity could have been the remnant of the progenitor. It's not clear to us if that's the case or not. There are a couple other dwarfs potentially associated with NGC 300, but they're really far out in the outskirts near the virial radius. One of which we also found with the Delft data, and it's a little unclear if it's even associated with NGC 300 or not. So presently, it does seem that whatever the progenitor is has mostly been kind of disturbed and is well within the merging process at this stage.
Okay, great. Thank you very much. Then I think we don't have any more questions in the room. So thank you, Catherine. Final talk by Lucia, and then we're going to have a brief led by Aritra. So please feel free to share the screen.
Hello, can you hear me well?
Yeah, great.
Okay.
Yep, go on. Thank you.
So, hi everyone, my name is Lucia. First, I wanted to thank you for giving me this opportunity to give this talk. I am on my final year of my PhD. I am working with the intra-halo light from an observational point of view. And I'm doing my PhD at ICRA, UWA. This is University of Western Australia, Perth, in collaboration with Aaron Robotham, Sabine Belstedt, and Luke Davis. So we already have a talk about from Sarah about the intracluster light or intra-halo light. So I will quickly introduce you this again. The intra-halo light is this diffuse stellar component, very faint, that is created within the multiple interactions that happen during the assembly history of the system. These interactions are mergers and tidal stripping, where the central galaxy steals material from the satellites, and all of these stars kind of end up mixed in this halo. And as Sarah was saying before, this is important as we can use the intracluster light as an extra tool to provide us with information of how was the assembly history of the system. So in my work, I use observations, and we face different challenges, such as the sky subtraction, because if we over-subtract the sky, we might be losing IHL information, the point spread function, because these scatter flags could be contaminating the IHL component, and the most important one is the galaxy decomposition, which the main two techniques that are used are the surface brightness limit cut, where we establish a surface brightness limit, where we say above this limit we have IHL, below this limit we have a galaxy, and the galaxy model subtraction, where we model the different components in the image, subtracted, and then we have the residual is the IHL. So it's clear here that we need deep and wide surveys. I will quickly compare HSC with LSST here. The size of the primary mirror from HSC is from Subaru telescope is 8.2 meters versus 8.4 meters of LSST. The filters in both surveys are GRZ-Y plus U-band in LSST. Then the field of view of HSC is 1.5 degrees versus 3.5 degrees in LSST cam. The survey coverage from the wide layer of SSP is 1200 square degrees versus a much larger survey coverage for LSST of 18,000 square degrees, sorry. And the R-band depth for the ultra deep layer of SSP is 27.7 versus 27.5 from LSST before coding. So because of these similarities between HSC and SST in the field of view, depth, and pipeline processing, all of my work could be easily, well, not easily, but applicable to LSST data. So as I was saying, I work with observations, and what we are doing now is developing an IHL estimation technique, which first we try to remove all the PSF scatter light from the image. So first, we have the original image. In this first step, which I'm not going into detail because I don't have enough time, but what we aim to do is remove the PSF scatter light from the IHL and kind of bring it back to the sources. We use our models for HSC PDR3, which are available here, publicly available here in my GitHub account, which is in this QR code in case anyone is interested. And the output of this first step is the PSF corrected image. And then the second step of this technique is actually estimating the IHL. So what we do is we mask the central galaxy with a surface brightness cut of 26.5 magnitude per square arcseconds. This is in the R band. And we aggressively mask, more aggressively mask the satellites. So what we do now is use Profit to fit a model of the IHL component. Profit is a two-dimensional galaxy fitting code where we assume a CERSIC profile of n equal 1 to fit the IHL component, and we leave free the parameters magnitude of effective radius. So after fitting these two parameters, we use Profit again to create the IHL model where we are assuming again a CERSIC index equal to 1 and the fitted parameters that we just obtained from Profit. So the main advantage of this technique is that we can extrapolate the IHL light towards the center, and we recover all of this light that was masked beneath the mask in the central galaxy. So I am currently testing this on mock observations. On the left, we see an HSC real image, and on the right, a mock observation of this group, where we are injected a different percentage of IHL following an exponential profile also. So these percentages go from 1 to 50%. This is what is found in the literature. And the idea here is that we recover the same fraction of IHL that we are injecting. And in this is from a particular group of galaxies, and the green points are the fraction of IHL recovered from the original image versus the orange one are from the PSF corrected image. So after applying the first step that I first showed. And the difference in the fractions here are very small because in this image there are no point sources. We know that the point sources are the ones that more contaminate the IHL, but also we found that the extended wicks of the PSF doesn't scatter so much flux because HSC was constructed to optimize LSB filters. So what we see in this plot is that at lower fractions, we are overestimating the fraction of IHL, and this is mainly because as the fraction is lower, this component is difficult to detect and to model, but towards higher fractions, this component is more prominent and is easier to detect. So the idea now is that I can improve these curves and try to follow the one-to-one line, mainly at higher fractions. And this is, I'm doing it with other mock observation, not from only one group. And after testing this plot or this tendency, the idea is to estimate the uncertainties in the technique. So after all of these tests, in the future, we are going to apply this technique to ultra-deep HSC PDR3 data, and we are overlapping HSC with gamma. So as you see in this plot, gamma are the red fields, HSC is the blue fields, and we're using gamma because we have this catalog, the Gamma Galaxy Group catalog, which give us information about the coordinates of the groups. So gamma and HSC ultra deep are only overlap in this small field called SXDS, and we have a nice sample of around 20 groups with more than 10 members. And we say this more than 10 members because the mass estimation from the catalogs are more robust when we use this limit. So here I am showing a few images of these groups of our sample, and these are made with G, I, and Y bands in the ultra deep data. And well, so this will be like this, the real application of the IHL estimation technique that I'm developing. So quickly, quick summary. I am developing this IHL estimation technique, which first corrects for the PSF scatter flux in the image, and then models the IHL component. Second, we are testing it on HSC PDR3 observation, that is current work, and in the future, we expect to apply this technique to gamma groups using HSC PDR3 ultra deep data. And finally, I wanted to take this opportunity to say that I am finishing my PhD soonish, so I will be looking for postdoc. So please reach me out if anyone is interested. Thank you.
Thank you. Lucia. We have plenty of time for questions, so.
Oh, that's a good question. Thank you for an interesting talk. As I understood it, your definition of the intercluster light is you've masked the region around the galaxy and you're looking at extended light beyond that and then fitting a Sursec and n equals 1 Sursec to that. So is there any, I mean, you have to choose a boundary where you, where the galaxy extends to, and your results may depend at some level on how you chose that boundary. Can you say a little bit more about that, or perhaps a misunderstanding?
Yes, we haven't measured the uncertainties of doing that yet, so I cannot comment that for now. Sorry.
Sarah?
Lucia, there's a related question. So Michael was asking about the like the extent of the galaxies. I'm curious about what extent of the group do you go out to? Because the intracluster light measurement's very sensitive to the radius you choose for that measurement. So I'm curious, what's your limiting radius?
You mean for the IHL or for the galaxy?
Well, for the IHL and the group light. So the measurement's very sensitive to that radius.
Yeah. Yes. So the radius that we are selecting depends on the surface brightness that we measure at that annually. So when we reach a value of surface brightness that is beyond the sky subtraction error, we discard that. We establish the limit.
And the group light, where do you take the group light out to?
So for the group light, we are using the 26.5 mask, surface brightness mask.
Okay, great. So that's all the time for questions we have. So let's thank Lucia again.
Thank you.
So we're just going to have a quick discussion.
So when Garreth and I were planning this session, we thought we could use the last 10 minutes to do a quick discussion on a possible data challenge in the broad things we have been talking about, either stellar galaxy structural parameters, galaxy morphology, low surface brightness features. And some part of this conversation started between members of both the Galaxy Science Collaboration and the ISSC during the last meeting that happened a couple of months ago. And so this is kind of continuing that forward and seeing what this crowd might have to contribute to that. So the basic idea is that, all of us have been talking about different kinds of algorithms, pipelines that we all like to apply on these data sets to do our science. But is there value on creating a common, either simulated or some other kind of ground truth data set when you can have multiple algorithms applied on that and then try to understand the biases of each of these algorithms, or at least try to compare them so that you can have a fair apples to apples comparison of not trying to figure out what is the best one, but trying to figure out what might be suitable for what case. So that's the kind of broad scheme in which we are trying to have this discussion. Some of you might have seen this paper. This was done by the Euclid collaboration, this was kind of a series of the Euclid preparation papers that came out. And what this paper did was essentially take simulated galaxies, simulated using single Cirsic, double Cirsic light profiles, and also realistic images generated using an autoencoder, and then applied a bunch of different algorithms on it and compared their results to see how they did. We planned earlier to have someone talk a little bit about it, but that fell through. So let me just pull up a slide from this paper, and I can kind of give you a basic idea for what we are trying to think about. So for example, this is done on, again, that entire data set containing both simulated light profiles and some semi-realistic profiles. And all of these are trying to get at the effective radius. And you have 5 different algorithms applied on this and trying to quantify their errors versus magnitude. So this is kind of what we are kind of hoping for. Now, so what we wanted to do is kind of get a sense from the audience on what this might look for if we did this in terms of grouping. If you could take a moment to join the Slido, and feel free at each question in the Slido, it's a multiple choice question, but just raise your hand if you want to say something about the discussion instead of just commenting there or putting your answer in there. Let's just give you a couple of minutes to join the slide deck. Okay. Most people in? Okay. So the first question is, do you think it's worthwhile, because these things take quite a bit of effort, of doing an LSST focused data challenge on either of these 3 things, on galaxy morphology, structural parameters, or low surface brightness? I especially want to, if someone is comfortable, like what I have heard arguments on why this should not be done. So if Robert.
I just want to know what the scope was. Yeah. The LSB, I'm much more worried about the instrumental effects than I am about our ability to recover the wings. So are you talking about the easy part, which is simulating galaxies using an autoencoder and recovering their properties? Or are you talking about the hard part, which is full-scale images with camera and scattered light and PSF wings forwarding like R⁻3? So that's why I said maybe.
So that's why we are having this discussion. So okay, none of this is defined in the sense that we are doing it, but it's a question of doing what would make it worthwhile. So that's kind of part of the discussion of what might be worth doing and what might be not worth. Okay, anyone want to contribute anything else?
I was going to add the effective radius comparison is kind of interesting, but I think once you add LSST type effects in, even more interesting. my personal interest is less on whether the effective radius is calculated correctly, but more on then the kind of second order, can we find features, probably less bars and spiral arms, but people are interested in that, but tidal features, that kind of next level, which is a slightly tangential question to the Euclid plot.
Yeah, the Euclid plot is just an example, but the point being, looking for even more features, substructures, things like this within the galaxy. Fine. Yeah.
So I think the problem I have with this is that it seems to me that there's at least two sets of data challenges here, and the level of complexity is very different among them. The types of questions you're asking, and as Robert pointed out, I think the level of fidelity you need for one of the set is very, very different from the level of fidelity you need for the other one. So I was also a maybe, but I may be now leaning to the yes, but not just one. Which of course makes our life hard. But yeah, it's hard to put everything into a single thought.
Yeah, no. So the next question might be appropriate. Let's try to. Okay. What would you want the data challenge or challenges to be focused on? And again, if none of these answers satisfy you, feel free to raise your hand and say something.
And so by morphology, you mean something like a Hubble type?
Pick your
I mean, what's the difference between a structural parameter and a morphology?
Structural parameters, I meant more prediction of structural parameters like radius, virtual light ratio, Cirrus indexes. Morphology would be getting substructure, getting like bars, spiral arms, or more coarser classifications. Okay, that's the difference between structural parameters and morphology.
This might be a biased audience.
Yeah. We just run this survey in multiple sessions and then we'll get some idea. Okay, so lots of interest in low surface brightness features. And we have heard within low surface brightness features, what are folks most interested about in terms of what would be, if you focus on two things.
Strings and shells.
What about LSBs themselves, the galaxies?
Yeah.
So galaxies.
So I think that's the hardest. This is the hardest one, right? Like, we can do morphological classification. It'll be interesting what morphologies we see when we have these large low surface brightness data sets. That's the hardest.
Any comments on this before I move on? I've forgotten what I said the next question, but yeah, in 3 to 5 words, what would be the most valuable aspect of such a data challenge for you? Let's assume we did this data challenge and think that you were best hope for that we did this data challenge. What would you expect to get out of it? Standardized comparison of algorithms, figuring out till what parts of the parameter space we can explore most effectively. So just in a few words, if you could describe what would be the best thing that you get out of such a robustness of algorithms, ground truth data.
We're not kidding about 3 to 5 words. It doesn't allow more than that.
That might be a limitation of the free version of Slido. Okay, so ground truth data, bitter statistics, robustness of algorithms, parameter space limits, establish standard definitions. Okay.
I would, yeah, because we don't have room there. Robustness of algorithms to the effects that Robert was talking about. All the